Hello everyone. I am Dr. Shikhar Tyagi from Department of Mathematics and Statistics, the University of the West Indies. I hope all of you are doing well. Today we are going to talk about the EM algorithm for the exponential distribution under the interval censoring. All right. So our aim is to discuss the EM algorithm under interval censoring. All right. So before going to the discuss the EM algorithm, so first we need to understand the interval censoring. So what happens in survival analysis, the exact event time is not always observed. So sometimes we only know that the event occurred between two inspection times, okay, between a limit of the or between the interval of a time it happens. So when we do not have the exact time periods, all right. So this type of incomplete observation is called as the censoring, or this is called as the interval censoring. All right. So, for example, suppose a patient is examined at the time 2 and again at time t, sorry, and time 3. If the event is not present at the time 2, but it is present at time t, then the exact event time is unknown. So we only know that it occurred in the interval between 2 to 3. All right. So this is called interval censoring. Or for another example, if we just take, suppose we have a light bulb is checked every week and it is working on Monday and failed on Friday. So the failure time lies between Monday and Friday. Or for another example, suppose you put 100 bulbs, okay, 100 bulbs on testing, and in that case, suppose you have the observation that first bulb was filled at time x1, second bulb was filled at time x2, and in that one, suppose x and bulb, when it was filled, you left the room, okay, at particular time, but when you came back inside the room, in the experiment room, you found that the xn bulb was failed. So in that situation, you do not know what was your exact failure time. So it was failed in between a time interval. All right. So suppose xn bulb, xn minus bulb was failed at that time, and you left out the room after that. And when you came back at that time, suppose x star n was the time when you came. So in between that, this bulb was failed. So the interval censoring was x n minus 1 and x star n time. That was your interval censoring. Another example we can take here, a student is tested every semester for a condition and it is absent in one test and present in the next. So the on test time lies between two tests. Another example is for the machine, a machine is inspected periodically and the failure is detected only at the next visit. All right. So this is the case of the interval censoring. So here, in this case, we are going to assume the statistical model. We are going to assume that let capital T denotes the failure time of the subject, denote the failure time of a subject under study. All right. So, and we assume that T follows exponential distribution with parameter lambda, and condition is that lambda should be greater than 0, then the probability density function, the PDF, the corresponding PDF is FT lambda is lambda into e raised to the power minus lambda t, where t and lambda both are greater than 0, and it should take the value 0 otherwise. Alright, so that will be your PDF of exponential distribution. Alright, and the corresponding cumulative distribution function, the CDF, everybody knows that the CDF of exponential distribution capital F T lambda is equals to 1 minus e raised to the power minus lambda t for all t and lambda is greater than 0 and 0 otherwise. Alright, and corresponding survival function, St is equals to e raised to the power minus lambda t. Lambda and t both are greater than 0. Alright, so now we will define the mathematical form of interval censored data. Alright, so what is your interval censored data? How you will going to define this one? So suppose for subject I, suppose the event time is only known to satisfy that the time I lies between Ti lies between the Li and less than equals to Ri. Ti should be greater than Li and less than equals to Ri. So here your Li is the last time the event was known to be absent. The event was known to be absent. Alright. And Ri is the first time the event was known to be present. Okay. So this is your interval sensor data. This is the definition of your interval sensor data, that Ti should lie between Li and Ri. So now we are going to drive the observed data likelihood under interval censoring. So what it will be? So the observed data likelihood under interval censoring. Alright, so what it will be? Since the exact time is not observed, the likelihood contribution is subject I. Contribution of subject I is the probability that Ti lies inside the observed interval. Alright, so in the writing, it will be since the exact time sorry, exact time is not observed, the likelihood contribution of subject I of subject I is the probability that Ti lies inside the observed interval. Observed interval such that probability that Ti lies between Li and Ri. That is basically from the property of the CDF, it will be F CDF at the limit Ri for the given lambda minus CDF at the value of T, that is Li with parameter lambda. So for the exponential distribution, it will be for exponential distribution, the probability that Ti will lie between Li and Ri is equals to 1 minus e raised to the power minus Ri lambda minus 1 minus e raised to the power minus Li lambda. When you will open the bracket, so minus will go with this minus 1 and minus minus will be plus. So 1 will be cancelled out. So what will be the final output we will have? It will be e raised to the power minus Li lambda minus e raised to the power minus Ri lambda. All right. So hence the observed data likelihood is observed data likelihood will be L lambda equals to product I goes to 1 to n e raised to the power minus lambda Li minus e raised to the power minus lambda Ri. The log likelihood corresponding log likelihood will be small l lambda equals to summation over the range of I goes to 1 to n log of e raised to the power minus lambda Li minus e raised to the power minus lambda Ri. Okay, so this likelihood is not as simple to maximize directly because each term contains a difference of the exponentials inside the logarithm. So that's why we need the EM algorithm here. So EM algorithm is designed for the incomplete data problem. So here the incomplete data are the interval censored observations, that is your Li and Ri, while the complete data would be the exact failure time Ti, capital Ti. So the complete data likelihood, if the Ti were known, so it would be the complete data likelihood would be L T in suffix lambda equals to product of I goes to 1 to n of e raised to the power lambda into e raised to the power minus lambda capital Ti, and corresponding log likelihood would be Lc lambda equals to n log lambda minus lambda summation over the range of I equals to 1 to n Ti. All right. So the EM algorithm replace the missing Ti by their conditional expectation given the observed interval. So the EM algorithm, how we are going to apply here. So it would be, we will start from the new page. We will define here EM algorithm. So let lambda k be the current estimate at the kth iteration All right. So in that one, we are going to compute the E step first. So E step will be, in E step, we compute conditional expectation, that is Q lambda, given that lambda's value at kth iteration equals to the expectation, conditional expectation of your complete log likelihood, sorry, it is L. Complete log likelihood for the given data and lambda's value at kth iteration. So it will be, since we have LC lambda is equals to n log lambda minus lambda summation over the range of I goes to 1 to n capital Ti. So we obtain Q lambda, given that at lambda's value at kth iteration it will be n log lambda, because n log lambda is independent from that one, from the expectation. These are constant, n is constant and lambda is constant, minus lambda summation over the range of I goes to 1 to n, expectation that we will apply the expectation here on Ti. Okay, so it will be expected value of Ti, where we know that Ti lies between Li and Ri with the lambda's values at kth iteration. Alright, so thus we need Ti cap at kth iteration, that is equals to expected value of Ti, given that Ti is lying between Li and Ri with lambda's value at kth iteration. Alright, so Ti is unknown here. So the conditional density of Ti given Li, Li is less than Ti and Ti is less than equals to Ri is, we need to compute. Okay, so first we just note down that the conditional density of capital Ti given Li is less than Ti and Ti is less than equals to Ri is Gi T given lambda raised to the power k equals to lambda raised to the power k into e raised to the power minus lambda at kth iteration into t divided by e raised to the power minus lambda value at kth iteration Li minus e raised to the power minus lambda's value at kth iteration into Ri. That will be the conditional density that we will get here. Okay. And it will basically Li is going to lie between T going to lie between Li and Ri. Alright, so therefore we can find out our Ti cap. I'm not solving this one because already you can solve it. The conditional density of exponential distribution. How to find out the conditional density of the exponential distribution when it is going to lie between this one, this interval. Alright, it is very simple. Okay. So it will be therefore Ti cap at kth iteration will be integral, because we need to find out this expectation, over the range of Li and Ri, because Ti is lying between Li and Ri. So into of integral over the range of Li and Ri, T into lambda raised to the power k, lambdas at the lambda's value at kth iteration into e raised to the power minus lambda value at kth iteration into t dt divided by e raised to the power minus lambda value at kth iteration Li into Li minus e raised to the power minus lambda's value at kth iteration into Ri. That is the value of your conditional expectation of Ti. Okay. So we need to solve this one. We need to find out the expectation. So what will be the expectation here? How you are going to solve this one? So just you solve it as you solve for the exponential distribution. All right. And after simplification, because this is a very simple integral that you can solve. All right, because lambda k will come out from the integral t into e raised to the power minus lambda k, lambda's value as kth iteration into t over the range of Li and Ri, that you can solve easily. So after simplification, I'm going to solve it. What we will get? We will get the value of Ti at the kth iteration. All right, so you try by yourself. If you are not able to solve it, then let me know. I will solve for you and I will simplify for you later if you are not able to do it. But you can, I hope you can do it by your own, because this is a very simple calculation. So what you will get the Li plus 1 upon lambda raised to the lambda's value at kth iteration minus Ri minus Li divided by e raised to the power minus, not minus, e raised to the power lambda at kth iteration into Ri minus Li minus 1. This is the expression that you will get after the simplification. Alright, if Ri is going to be up to infinity, that can be possibility. So there is one possibility that Ri is equals to infinity. Then Ti cap, so Ti's value at kth iteration will be Li plus 1 upon lambda value at kth iteration. Alright, and remaining terms will be 0. Alright, now we are going to maximize this one. That will be our M step. So now maximize Q lambda given lambda's value at kth iteration equals to n log lambda minus lambda summation over the range of I goes to 1 to k of Ti cap at the kth iteration. Now differentiate with respect to lambda. Okay, find the derivative with respect to lambda and set it equals to 0. Alright. So when you are going to find out the derivative, partial derivative with respect to the lambda of q, it will be n upon lambda. Okay, this portion and log lambda is 1 upon lambda minus this portion will be minus summation over the range of I goes to 1 to k Ti cap k. Ti cap k is basically the value that we got from here. Okay, if Ri is not equals to infinity and put it equals to 0. So from here you will get that lambda's value at k plus 1 iteration will be equals to n upon summation over the range of I goes to 1 to n Ti cap at the value of kth iteration. Alright, so or you can say that lambda's value at k plus 1 iteration equals to n upon Li plus 1 upon lambda's value at kth iteration minus Ri minus Li divided by e raised to the power e raised to the power lambda kth iteration Ri minus Li minus 1. That will be the values of lambda's value at k plus 1 iteration. So this is your maximization step and this is your expectation step. This is the formula of the expectation for your exponential distribution. All right. So this was the EM algorithm for exponential distribution under interval censoring. So in the next lecture, we will discuss about the some numerical examples and the R coding of this problem, EM algorithm for the exponential distribution under interval censoring. We will solve one numerical question as well as we will solve the R coding. So thank you very much for your attention for this lecture. We will see you in the another lecture. Subscribe for the further videos. Thank you very much.